Okay, so it's not, oh, it's recording now. All right, so basically this is where we're at. We've covered relative velocity. I'm going to do one more topic about relative velocity, which is instantaneous center to zero velocity. I'll complete the example I was doing yesterday, but just to highlight, next week is this, the accelerations. And so again, one of the goals in this course is to deal with second law. Either it's Newton-Euler or Newton's second law, and we need acceleration. So you're going to need these terms later for the kinematics. And just briefly, all of the other motions are subclasses of this. So if you want translation, you just get rid of VA with respect to B. If you want rotation, you get rid of VB. All of this sort of comes down to this one fundamental equation. And the problem is that we may be breaking it up too much. That's a personal opinion. Okay. Now, as a reminder from yesterday, we were dealing with this problem. We have a link AB and another link BC and a slider at position C. C is limited to move left or right. AB is rotating about point A. However, BC, that link, is going to undergo general plane motion. So right now I have rotation. Translation. And general plane motion. So all of that is what you have to think about. And when you do the analysis here, you never ever look at the link BC before you look at the other two. So you'll notice that in the analysis I did here, and I used the vector approach for this part of the problem, I just said, hey, I just want to know what the velocity of B is, velocity of C is. I know what the velocity of B is in terms of A, because that's rotation. And once I know what the velocity of point B is on the link AB, I know what the velocity of B is on the link BC. Over here, when we calculated the final solution, I also knew that velocity of C is translating. So it's moving in the I direction. It's plus or minus, but it's only limited to that. So when I did my vector solution, you'll notice I have VCI, not VCJ or VCK. Same thing with all of the rotations. Rotations in this course are nice. They only occur about k. So omega ABK, omega BCK. And what I need to know to solve this problem is not the direction of the velocities. I just need to know the directions of the link. So I solve for the link position, A sine theta, A cos theta, and the link position minus B cos phi and B sine phi. Now, as you're going through these, there's, again, two different approaches, and I'll talk about a third approach today, the instantaneous center of zero velocity, which I have spoken about as enthusiastically as I ever will just now. I think it is important that as you're doing these problems, as you're preparing for the midterm, that you do draw these things out. Draw them as much as possible, write out your equations as much as you can. But if you were to solve this same problem as a graphical approach, we can start with the same thing as we had before. We can take a look at A and B. And when we look at A and B, recognize that we have fixed point rotation, and velocity of B has to be normal to the link AB. So I know the direction of rotation that's given to me, but I also know that that's going to be at 90 degrees. Now, one of the problems I have with the graphical approach is I have to know the orientation of velocity vectors. When I'm looking at a vector solution, I only need to know the positions of the various parts of the mechanism. So I need to rotate this by 90 degrees. So I have velocity of B and it's going to be velocity bx, velocity by, and I can do the same thing as I did with my vector solution. And just write all of the terms out. And recognize that the velocity of A is 0 because there's no translation of the pinpoint. There's a lot of physics in this. We're taking sort of the geometry, looking at what's happening, but we have to recognize how things are sort of moving. So from this, I can write these results. And again, I kind of have x and y, my coordinate system over there, and I know what the directions are. Now again, what you'll notice is that I have to know the directions of all of this stuff, and I'm not going to use a sign where I might normally have done it with the vector solution and a cosine over here. So as you're going through these problems, as you're writing all of this up, you also have to know the direction of all of the terms. So if you don't draw that out, you won't necessarily catch that that's negative. So now I have the velocities at point B. I can go back to this. And this is where it gets confusing for me. Here. I need to know the direction of velocity B on the link BC. Now, the magnitude, that I already know, the direction I already know, but I'm going to reference it relative to this link. So velocity of C is still limited, maybe not that. Velocity of C equals velocity of B plus velocity of C relative to B. Velocity of C, and this is link is B, y equals, oh, sorry. Now, I know from the previous part of the problem, I might not necessarily do this in advance, but I would have probably guessed at this point the direction of velocity C. Now, I have to guess the velocity C direction, and intuition in my case works really well because one, I solved it already, and two, I've seen enough of these problems. But this is hard to do. So when you deal with a graphical solution and you have to guess the direction, you're pretty much going to have to decide whether it's forward or backwards. But when you do that, you end up oh, sorry, that's not what I wanted. you get that the velocity at point C with respect to B has to be normal to the link. And so this velocity at point C has to be normal to here. So you got a y direction down and a negative VCBX. So putting all this together, you end up with minus B omega BC sine of phi, VCBX equals minus B omega BC cos of phi. If you solve through and if you have all of the directions correct, you can then write the same equation as you just solved for in the previous part of the problem. And you'll end up with the same governing equations as you had before with the same velocities. And if you do that, you'll end up with the same numbers. I have long felt if you're doing an introduction, or if this is your introduction to this type of motion, rigid body kinematics, vector approaches often are much simpler. And vector approaches are simpler because you look at the geometry that you're dealing with, not the motion. But different people, different opinions on this. So I strongly recommend, again, lots of time over the weekend, and we got next Thursday, everything's going to happen. You got time. Try to do these examples on your own to convince yourself which way is the better way to do this. But you don't just look at the problems, do them. Okay. Lecture 21. No. All right, so again, this course is a very funny course in the sense that we do not have three-dimensional motion. There's no rotation about any other axis than the z-axis, and whether I put it in the yz plane or xy plane, it doesn't matter. It's always going to be normal to the sheet of paper or the screen that you're looking at. And the other nice thing about planar motion is that you always have a point which is called an instantaneous center. And we talked about this yesterday to a certain extent when we were looking at, well, actually Monday and Wednesday, when we were looking at rolling without slip. And I'll start with that again. So I have a wheel and it's rotating. Omega naught. Yeah. And I can define a normal direction, tangential direction. I can define everything with respect to the motion that's occurring. And if I look at that point of contact, Q, should do one more thing. No. if I look at a point in contact with the ground and I roll a wheel along it, the point of the wheel that's in contact with the ground and the ground's point of contact with the wheel, which are P and Q respectively, have the same velocity. And one of the things you'll do a lot of is you might have a conveyor belt where you have a belt moving with velocity V naught, in which case Q is moving with V naught, then P is moving with Q naught, or V naught. But the important point here is that velocity of P, now since it's 0, it's just 0. Velocity of P equals velocity of Q. And so both of them sort of are there. I'll try and do better. And so if I have, say, a wheel that's rotating around and it's moving forward, V naught and omega looks like that. And I can define again, and really important, if you do anything with vectors, make sure that you do this, which is to just put your positives down. So x is positive to the right, y is positive up, and counterclockwise is negative. Or sorry, counterclockwise is positive. Omega the wheel. So if you're looking at a situation like this where you're saying, oh, hey, I want to know what the velocity of point P is, I can say, well, it's velocity of O plus omega of the wheel crossed with RP with respect to O. So velocity of O I know, but RP with respect to O is equal to minus Rj. So from O, down to point P, I will have a negative distance. You can rewrite it this way too. Both ways are the same thing, but one of the things that comes out is that the velocity again in point of contact now is 0, which is kind of, again, it's kind of a neat result. It's sort of something you think about, but it's not important. You can solve all of the problems I'm about to do using vector approaches, or you can use instantaneous centers. We're going towards instantaneous centers. So now, I always know that when I'm dealing with a wheel and it's rotating, the center is always going to translate. It does not rotate. It doesn't move up or down. Every other point on the body will move up and down. Really close to the center, it'll sort of do this. Way from the center goes up, down, up, down. If I solve through for that, I can say, well, omega of the wheel, whatever it is just going to be omega of the wheel k, because I know, again, I've got planar motion. I've got all of the distances associated with this, and I have all the terms that I need. So 0 is equal to velocity naught plus omega wheel crossed with r p with respect to O. And because of the way I've defined it, and I probably should have been a little bit more clever and just made it positive to start with so that I would get the correct answer again, but I've started with this as a clockwise rotation because I know it's a clockwise rotation. But had I substituted in a positive counterclockwise as my guess, you'll see that this will sort of work out. And you end up with omega naught is equal to, maybe just do one more step. 0 equals V naught I plus omega. And that's, I'm trying to decide if I should put in the extra step, but maybe it's a good idea. Omega wheel k crossed minus r j omega wheel k r times I. Okay, I'm kind of jamming a lot of stuff in there, but I just wanted to show the middle steps here. And so I've kind of put all of that together. I end up with my solution is a little bit different with this, and my omega wheel in this case will be in the correct direction. So I'll get omega of the wheel is equal to V naught over R in the k direction. But this is a clockwise, and so it's rotating like this because I put in the correct sort of magnitude of terms and all of that. When you do cross products, when you do all of this stuff, it's going to work out really nicely. If you don't, good luck. So what that kind of says is, hey, this is kind of interesting. I can define a body like this and say, hey, what happens if this is 0? Then instantaneously this entire body is rotating about that point. Instantaneously. It's not continuously. I'm not pinning the point at that instant. I'm just doing it at 1 second or 1 instant in time. So say, for example, I have Q here, I've got C, and I have a distance which is given as RC with respect to Q, and I have velocity of C. If a rigid body is rotating instantaneously point Q, the velocity of point C is velocity of C equals velocity of Q plus velocity of C with respect to Q, which equals velocity of Q plus omega of the body cross with RC with respect to Q. And those 2 points go away. And if they go away, everything is just fixed point rotation. Now, the other thing that you don't have to have with this is, in this case, for example, I started out the lecture, or this part of the lecture, by showing this diagram and showing that that instantaneous center is not part of the body. It doesn't necessarily have to be the same as, or any part of the body. It's not a physical point, it's an instantaneous point. The other thing is that an instantaneous center of zero velocity is an instantaneous center of zero velocity, not an instantaneous center of zero acceleration. So next week when we talk about acceleration, I can't use these ideas. If the velocity of q is 0 for all time, q is the center of rotation. If the velocity of q is 0 for an instant, then it's an instantaneous center of zero velocity. And I'm going to always stop writing all of that and just put ICZV. Okay, so I have two choices. Generally, when we're dealing with problems here, we're going to see instantaneous centers. Okay, for any type of planar motion, you will always have an instantaneous center. They always exist. As you go into third year dealing with robotics and you're dealing with three-dimensional motion, good luck. That doesn't hold true. And all of this stuff, this approach doesn't work. The vector approach does. So everything you're doing with vectors works all the way through. Graphically, I can't visualize 3D motion. So if you have only a couple, which I consider really easy cases to consider, where, for example, you have a falling rod. That is a rod that's dropping, and it's sort of in a corner. And in that case, you have an instantaneous center of zero velocity that's there. And it's easy to define, and it's often easier than any other approach. Because in that case, I just look at the geometry, say, hey, look, there's where it is, and it's all going to work out. I also know what the direction of rotation is. It's counterclockwise. I don't necessarily know what the magnitude is at this point, but I know enough from that. And as it falls, that instantaneous center is going to shift. Yeah, I can do that. And I need to recognize that this is all geometry dependent. So at instant 1, at time 1 at the top, is not the same instantaneous center as time 2. You also end up in very particular cases. You'll see them in some of the old quizzes, I think, maybe some of the newer ones, where you have at some instant in time an object that's rotating, so a 3-bar link like this, and those two vectors are the same magnitude and the same direction. And so if I draw perpendiculars off of this, they never intersect. So even though this system is rotating, this bar is translating. And you need to spend time on this kind of problem too. You need to sort of think about, hey, how's that sort of working out? Because it's actually kind of useful to you. You also have a secondary case where you have a falling rod. Again, if you draw perpendiculars off of it, it goes off to infinity, and there is no rotation. So omega in both of these cases, let's say AB, AB, omega AB equals 0 here and here. I'm going to try and do an example of this with a gear that I have. I don't know if I will. Nope, there we go. But basically, another common sort of case is a wheel that is between two walls. And so the walls have a velocity A and a velocity B. And when you're dealing with problems like this, you need to recognize that your instantaneous center is not the geometric center of the object. So this wheel is being sort of pulled on the top and on the bottom. They have two different velocities, and so it's not symmetric, but the geometry that you'll see is going to be shifted. So velocity of A over HA, HB is equal to velocity of B over HB. HA plus HB equals 2R, and V1 over omega wheel plus V2 over omega wheel equals 2R, and then there we go. Omega wheel is equal to V1 plus V2 over 2R. So in very specific cases, this is really a powerful technique. Applying it everywhere is a really bad idea. Don't do this with everything. But if you got something like this, you can do that. And I end up not doing it with something else, but there you go. You also have another case where you might have, say, again, a wheel, and you have this, and you have this, and you drop a perpendicular off of that, and I'm going to make my life easier. Velocity 2, or A, velocity of B, and your IC, again, is way off of the body. It has no contact, or no relation to the physical body, but it has a relation to the kinematics of this system. And in that case, you kind of say, okay, I've got 2R for this. I have H to here, VB over 2R plus H is equal to VC over H, which equals omega of the wheel. H is equal to 2R VC over VB minus VC. And you can also say that omega of the wheel is equal to VB minus, I should call it A. VB minus V. A all over 2R. Geometry is really powerful. You can do a lot of things with it. We did it at the very beginning of the last lecture the Monday lecture, where we were looking at absolute motion and geometries. You can do a lot of things with this. I don't necessarily, unless you have really kind of a simplified case like this, I really wouldn't do this approach for most. I wouldn't do any of these approaches. There we go. All right. Okay. Am I going to be able to do this one? Maybe I don't want to do this one yet. I'm actually going to do a version of this problem later, so I'm going to, I might do this one. So this one's similar to what I'm talking about today, and I'm not going to do it the way I just said I should do it. Okay, at the instance shown, the lower rack moves to the right at 2.4 meters per second, while the upper rack moves to the left at 1.3 meters per second. If the nominal radius of the pinion, O, so that gear, is 0.2 meters, determine the angular velocity of the pinion as well as the position of the pinion's instantaneous center of rotation relative to point O. All right. There you go. So moving to the right, moving to the left. And I've got, there we go. So I've cleverly used V sub L for the lower velocity, V sub U for the upper velocity. And the center of geometry here, and it's really important to remember that, is that it has nothing to do with the center of rotation. And so the green point is the center of rotation. The yellow point is the instantaneous center. Now I know that's going to be where it is, and I could calculate it based on what I have there, but there you go. So velocity up, velocity lower, and the other thing that I know is that both of these are constrained to move in the x direction, so I. So upper direction is going to be negative, and the lower direction is going to be positive. So I can reference everything between the upper and lower parts of this gear. And if I do that, I can say, well, velocity on the upper side is equal to velocity on the lower side plus that rotational component. And it's going to be omega k cross with the distance from U to L, or U relative to L. And if I do that, I'll end up with sort of not having to write this, 2rj. Because if I go and reference everything with respect to L, that distance is going to be positive. So down at the bottom here, to get to L, or to get to U, I have to go up. And because I'm going up, I have a positive value. So I end up with minus VU in the I direction is equal to VL in the I direction, and after doing the cross product, minus 2 omega p r in the I direction. And no surprise here, I get the same relationship as I had before, which is going to give me 9.25 rads per second in the k direction. This is the same relationship we just derived with geometry coming out of the vector relationship. So all of these approaches give you the same information if you do them correctly. You're less likely, if you're dealing with the geometry, to make a mistake. So there you go. Now, the other thing that's important to keep in mind is that the velocity of the instantaneous center, we know that's going to be 0, is equal to the velocity of the lower plus omega p, which I've just calculated, cross with RIC with respect to the lower distance. Now, I don't know what that distance is. I know it's positive j. That's the only thing I know. I don't know anything else. I do know that if it's an instantaneous center, though, it's 0. So if it's 0, I can say 0 equals VL in the I direction plus omega p k times x I c in the L in the I direction, y I c in L in the j direction. Now, I'm putting all of the terms in because I still have to. I don't know exactly. It might be off the center. But if I do that, I'll end up with two equations. One, which is 0 equals VL minus y IC with respect to L omega p. And another one, which is 0 equals x I c with respect to L omega p. And that's my I equation. That's my j equation. So I know from that omega p, which I've just calculated, is not 0. So that has to be 0. And it's symmetric. I kind of knew the answer to that one right from the beginning. But on the other side, I don't know where YICL is. So I do have to sort of say, well, VL over omega p equals 2R VL plus V upper, which equals YIC with respect to L, and RIC with respect to L equals 2R VL plus V upper after sort of substituting all the terms in, and it's in the j direction. This is a good problem to practice on. One, you can use the technique I just talked about with instantaneous centers. Everything sort of works out. You could actually calculate the instantaneous center directly, but if you approach it from a vector approach, you also get the same result. You could do it with graphics too. Good for you. But in all of these cases, as you're doing these problems, think about what the results are and what the physics are. It's hard to visualize these motions. Excuse me. Any questions on that one? Let's do one more with rolling without slip. Oh. So, just as an aside, you know this already. You've seen it in a lot of forms. I may not have put the law of tans up, but generally it's really good to sort of know what the laws of sines, cosines, and tans are, just because you can use them for calculating terms dependent on what you have. And so coses, sines, and tans. Nobody ever puts tans up, but it's kind of useful to know. And if everything works out, I'll have everything. This is kind of annoying. Oh, I have this one. This is good. Okay, wait. Maybe next week I'll do that one. So next week I'll do some more acceleration problems. And I may do one of the sort of funky ones. Okay. A truck is moving with a velocity of 15 kilometers an hour while the pipe section of radius r of 1.35 meters and center at C rolls without slipping over the truck's bed. The center of the pipe section is moving to the right at 2.7 meters per second relative to the truck. Determine the angular velocity of the pipe section and the absolute velocity of point C. Okay. So again, it's really important that as you solve these problems, you actually you write out what you have and all the terms that you have for that. So if you do that, you can say velocity of C is equal to velocity of Q plus velocity of C relative to Q, and you can sort of do that. Got C, I've got Q, everything is aligned. I also know what's happening there. Okay. Now, velocity of C with respect to Q is in the I direction. It's moving to the right. It's not bouncing up and down. So I know that direction. As usual, and I may stop writing this, I probably should, omega is going to be in the K direction, omega pk. So RC with respect to Q, again, it's positive because of the way I've defined my coordinate system. It's up. And it's R of the pipe. And I can write out that the rotational velocity, Vc with respect to Q, is omega pk rj. And VCQ equals minus R omega P, and omega P is equal to minus VCQ over R. There we go. Okay. Now, one of the things I've done in all of these examples today, yesterday and Monday, is I've never really talked about this angular velocity, but you'll notice I only calculate it once. And when I only calculate it once, what I'm doing is I'm saying that, in fact, it's the same angular velocity no matter what I do. So if I calculate it for another point on the body, I better get the same result. If I get a different result at 2 points of the body's splitting apart. So omega is going to be constant on these objects. So I have that, And using the values given, I can find immediately that omega is equal to 2 rads per second. And the other thing that I tend to do is, even though units or rads are unitless, they're really good to keep within your calculations. Okay. And V sub C equals V naught I plus omega pk cross with rj, and if you substitute all the numbers you were given,